So in this class, we are basically going to see two presentations. First, it will be given by Tathagata, and the second, it will be given by Anuvab, and both of them will talk about prime number theorem. And in our previous class, we have already seen the two presentations that was on Mobius inversion function given by Pratik and Shubhrodip. So both of them, they did really well, and I expect that today also both Tathagato and Anubhav, they will also do the same. So without having any delay, let's welcome Tathagato for the first presentation on prime number theorem. So Tathagato, could you please share your screen and all?
Yes, sir. I am starting to share my screen.
Yeah, please. Yes, it's coming.
My screen visible to all?
Yeah, it's visible and audible as well.
Yes. So let me start now.
Yes, please.
Good morning, everybody. Today I am going to talk about prime number theorem. And before starting this lecture, we must know that what is the motivation to study this prime number theorem. Basically, the main motivating question in this topic asks, how are the primes interspersed among the natural numbers? That is the distribution of primes in the natural numbers. As a first step, we know from Euclid that there are infinitely many primes. And this theorem, there are infinitely many prime numbers. And all of you know this theorem, and its proof is very easy. Though I recall this proof, that suppose that there were only finitely many primes p1, p2 up to pk, then consider the integer n equals to p1 into p2 into up to pk plus 1, and this number is not divisible by any of the pi. It has remainder 1 upon the division. However, by fundamental theorem of arithmetic, it must be divisible by some prime p. Since this p is none of this pi, we have a contradiction, and because we must not have written down all the primes, and this is a very easy proof. And the same proof shows that there are infinitely many odd primes, because all of you know that 2 is the only even prime and all the other primes are odd. So basically there are infinitely many prime numbers of the form 2k plus 1, that is odd primes. And we can prove easily that there are infinitely many prime numbers of the form 4k plus 3, and you can see this proof in any number theoretic book, and I avoid this proof in this lecture. In fact, these are the special cases a b equals to 2 comma 1, and if we write this in the format ak plus b, then here is a equals to 2 and b equals to 1, and here is a equals to 4 and b equals to 3, and from here there is a much stronger statement, and this is Dirichlet's theorem. And this theorem tells us that if a and b are positive integers, not divisible by the same prime, look very carefully. A and b are positive integers and they must not divisible by the same prime number. Then there are infinitely many primes of the form ak plus b. And all of these cases are the generalizations of this theorem. So, and the proof of this theorem is difficult, and I think this is out of the scope of this course, and so I avoid this proof in this lecture. But my favorite theorem of this type, for which we do have an elementary proof, is the following. it provides yet another proof that there are infinitely many primes. So now let us come to a very interesting theorem that tells us the sum of the reciprocals of the primes diverges. That is, summation 1 by p tends to infinity where p is prime. And all of you know that the summation of all the reciprocals of all the natural numbers is also diverges, and in this theorem we will prove that the sum of the reciprocals of the primes are also diverges, and this is a very nice proof. And before starting this proof, we will need the following tools for the proof. And let me enlarge the screen. Yes, we will need the following tools for the proof. And this is the tool 0. That is, the first point is the fundamental theorem of arithmetic. And this tells us that we can write any natural number n equals to p1 to the power alpha 1, p2 to the power alpha 2, up to pk to the power alpha k, where all these p1, p2 up to pk are primes. And the second point is 1 by 1 minus x equals to, this is a power series expansion, this equals to 1 plus x square, and in this form x to the power n and goes to infinity number of times. And the third point, that is indicated by 2, this is log 1 minus x, and this is a Taylor series expansion, and this is also an infinite series, and we can write it minus x square by 2 minus x cubed by 3 up to minus x to the power n and so on. And this is the harmonic series 1 plus half plus 1 by 3, and I tell you just now that this series is diverges. And you learn this proof in the basic real analysis course. Tools 1, 2, 3 were introduced in calculus. Recall that the series summation 1 by n to the power s diverges if and only if s equals to 1. If and only if s greater than 1, if and only if s greater than 1. And you also learn this proof in the basic real analysis course. Now let us come to the main proof. Let n be a natural number. We define the following product, lambda n. Lambda of n equals to, we define this in this manner. This is pi, or you can call it the products of p less equals to n, that is the prime numbers less equals to n, 1 by 1 minus 1 by p. Suppose you take n equals to 5, then the prime numbers less equals to 5 are 2, 3 and 5. So this lambda of 5 will be 1 by 1 minus 1 by 2 into 1 by 1 minus 1 by 3 into 1 by 1 minus 1 by 5. And our first goal is to prove that this lambda n diverges. To see this, note that we can rewrite each of the factors as an infinite sum using tool 1. Look at the tool 1 and replace this x by 1 by p, and you can see easily that this will be equals to 1 plus 1 by p plus 1 by p square. And look at here, I write this lambda n equals to, for p equals to 2, we can write 1 plus 1 by 2 plus 1 by 2 square and up to in this way. And for p equals to 3, we can write this 1 plus 1 by 3 plus 1 by 3 square, and in this way for p equals to 5. And for other primes less equals to n, we can write this in this format, and these are the products of this series. So when we expand this product, we will obtain all the fractions of the form. Suppose I expand this product and we get the terms just like, suppose I 1 by 2 into 1 by 3 into suppose 1 by 5 square, And look at this is the general form of all of these terms. 1 by 2 to the power alpha 1 into 3 to the power alpha 2 up to pk to the power alpha k. And here you can easily check that 1 by 2 into 1 by 3 into 1 by 5 square. Then this alpha 1 will be 1, and 3 to the power alpha 2 will be 1, and 5 to the power alpha 3, and this alpha 3 will be 2, and all the others alpha I, that is alpha k, and these will be 0. So where all prime factors less equals to n appear, and by the fundamental theorem of arithmetic, we will get all the prime numbers 1, 1 by 2, 1 by 3 up to 1 by n, and many more. And if you see it carefully, then you can observe that this lambda n contains all the terms 1, 1 by 2, 1 by 3, and also there are many more terms. So this lambda n is easily greater than 1 plus 1 by 2 plus 1 by 3 up to 1 by n. And hence, as n tends to infinity, this lambda n tends to infinity by tool 3. See this tool 3, and this tells us that this harmonic series is diverges, and as this lambda n greater than this series, so this lambda n is easily tends to infinity when n goes to infinity. In particular, this means that log lambda n tending to infinity as n goes to infinity, because all of you know that when n goes to infinity, then log n also tends to infinity. Now our second and final goal is to relate lambda n with the series summation 1 by p. To do this, we take logs. By basic properties of logs of products and reciprocals, we obtain log lambda n. Put just simply log here, and this will be log lambda n, and this will be summation p less equals to n minus log of 1 minus 1 by p, because this is in the product format. And by using the formula of logarithm, we can write log abc equals to log a plus log b plus log c, and also log a inverse equals to minus log a. And see it carefully that here every term is in this form 1 minus 1 by p whole inverse, and this is in the product format, so we can write this term in this way. And now using tool 2, let us come to the tool 2, and it tells us that what is the series expansion of log 1 minus x. And now we can write minus log 1 minus 1 by p and replace this x by 1 by p, and look carefully that this will be 1 by p plus 1 by 2p square plus 1 by 3p cube plus 1 by 4p to the power 4, and so on. And this minus is cancelled out by this minus, and this will be plus before every terms, and so we finally obtain this term. And you can see easily that this series is less than 1 by p plus 1 by p square plus 1 by p cube plus 1 by p to the power 4, and so on, because if you compare 1 by p square and 1 by 2p square, you can see easily that 1 by p square is greater than 1 by 2p square, 1 by p cube is greater than 1 by 3p cube, and so we can write it in this way. And now I take common 1 by p, and I get 1 by p into 1 plus 1 by p plus 1 by p square, and so on. And this is the infinite sum of the geometric series. Look at this. This is the infinite sum of the geometric series. So I can write it 1 by p into 1 by 1 minus 1 by p. And all of you know that suppose the sum of the series a plus a into r plus a into r square up to infinity, where this r is 0 less than r less than n, and this sum will be a by 1 minus r. And look at this series here, this a equals to 1 and this r equals to 1 by p, and this 1 by p is strictly less than 1. So this will be 1 by p into 1 by 1 minus 1 by p, and this equals to 1 by p into p by p minus 1. And you can check easily that this p by p minus 1 will be less than 2. So this term will be finally less equals to 2 by p. But then this means that log lambda n less than summation p less equals to n 2 by p. And we put the value of minus log 1 minus 1 by p in every term of this summation series, and we get finally that this term log lambda n less than summation 2 by p. Since the left hand side, that is log lambda n, diverges, we prove it here that log lambda n tends to infinity as n tending to infinity. So since the left hand side diverges, we have that summation p less equals to n 2 by p diverges. Division by 2 yields the result. So our final result is summation 1 by p tending to infinity when n tending to infinity, because this log lambda n is diverges when n tending to infinity, and we prove it just now. And this is a very nice proof, and this theorem is somewhat surprising, since for instance the sum 1 plus 1 by 4 plus 1 by 9 up to so on, that is the sum of the series 1 by n square, where n is the natural number, each converges, and you prove this result in the basic real analysis course. Yet we prove just now that summation 1 by p diverges. Hence it might be appropriate to say that there are more prime numbers than square numbers. However, this sentence is pure nonsense without a proper definition in mathematical logic. Along a different track, one way of measuring how many prime numbers there are is to consider the fraction of natural numbers that the prime comprise, and consider the function pi of n equals to number of primes p less equals to n, and this pi is not similar to the pi we use in geometry. And here is some examples. Pi of 5 equals to 3, because the number of primes less equals to 5 are 3. These are 2, 3 and 5. Pi of 100 equals to 25, and pi of 5000 equals to 669. And here is an important observation, is that the density of primes up to first 100 natural numbers is 25%, and the density of primes up to first 5000 natural numbers will be very, very less than this 25%. So we can see that the density of primes is gradually decreases. In 1850, Chebyshev proved that there exist real numbers C1, C2 with 0 less than C1, less than 1 less than C2, such that C1 into n by log n less than this pi of n, and this less than C2 into n by log n. And this is a very important theorem to prove the prime number theorem. And now let us come to the prime number theorem, the main theorem of this topic. The prime number theorem tells us about the asymptotic behavior of pi of x, that is, the behavior of pi of x as a function when x is very large. So all of you know the meaning of asymptotic.
Tathagata, please skip this part. I have discussed, as I also have this part.
Yeah, but I discussed the asymptotic nature, and you we'll discuss the other parts. So although all of you know the definition, although all of you know the concept of asymptotic, but I see you what is meant for asymptotic. Look at this. Yeah. What is meant for asymptotics? Suppose f of n equals to n square plus 3n. Then as n becomes very large, the term 3n becomes insignificant compared to n square. The function f of n is said to be asymptotically equivalent to n square as n tends to infinity. And we can write this as f of n is equivalent to n square, which is read as fn is asymptotic to n. Formally given functions fx and gx, we define a binary relation f of x is equivalent to g of x as x tending to infinity if and only limit x tends to infinity, f of x by g of x equals to 1. Now in the prime number theorem, we can also write pi of x is asymptotically equivalent to x by ln x if and only if limit x tending to infinity, pi of x by ln x equals to 1. And Anuvab will show you how this theorem, how this result comes. And now came to the main lecture. Yeah. And Anuvab will also tell you the machinery of the proof of the prime number theorem, and he will also tell you the similarities of this prime number theorem, that is the distribution of primes with some natural phenomena. So Gauss, one of the most influential mathematicians, conjectured in 1793 that the value of pi of x is very close to the value of the more familiar function Li of x equals to integration 2 to x dt by log t, in the sense that pi of x by Li of x tending to infinity as x tending to infinity. This was later proved by Hadamard and de la Vallée-Poussian in 1896 and is known as the prime number theorem. And this is the elementary proof of the prime number theorem, and this proof is very, very large. And later Newman proved this prime number theorem by using some tools of complex analysis. And as we have not yet studied this complex analysis, so we can't give this proof in this lecture. So the proof is beyond the scope of these notes. By applying L'Hospital's rule, one can observe that limit x tends to infinity, Li of x by log x equals to 1. And I will show you how we obtain this result by use L'Hospital's rule. So look at this. Yeah. So limit x tends to infinity, Li of x by ln x. And you see that this Li of x equals to integration 2 to x dt by ln t. And if you check that this is infinity by infinity form, so we can use L'Hospital's rule and differentiate both of these terms. And this ddx of this integration will give you 1 by ln x into ddx of x, and ddx of x will give you 1, and this minus 1 by ln 2 into ddx of 2, and as 2 is a constant, so you get 0, and finally this differentiation will give you 1 by ln x, and you can see easily that this will be ln x minus 1 by ln x whole square, and I can write this in this way, and this will be finally limit extending to infinity ln x by ln x minus 1, and this is also infinity by infinity form, and so we can again differentiate both of these terms and get 1 by x by 1 by x, and finally we obtain this equals to 1. So we now came to the main lecture. So we proved this result by using L'Hospital's rule, And this is the prime number theorem, can be restated as in this way, and Anubhav will discuss you more briefly all of these things, so I skip this. And now here is an important remark. Already we have shown that there are infinitely many primes. Now the following theorem will show that there are no primes in arbitrary long runs of integers. So let us come to this theorem. Given any positive integer n, there exist n consecutive composite integers. And this theorem satisfies for any larger value of n. And now let us come to the proof, very easy proof. Consider the integers n plus 1 whole factorial plus 2, n plus 1 whole factorial plus 3, up to n plus 1 whole factorial plus n plus 1, that is here are total n terms, and every one of the above integers is composite. Because if you look at this term, this is 1 into 2 into n plus 1 plus 2, and this is divisible by 2, and similarly this will be divisible by 3. And in general, since j divides n plus 1 whole factorial plus j, if 2 less equals to j less equals to n plus 1, and we proved this theorem. And here is an example. Note that 8 factorial plus 2, 8 factorial plus 3, and 8 factorial plus 8 are 7 consecutive composite integers. However, these are much larger than the smallest 7 consecutive composites, 90, 91, 92, up to 96. So these 7 composite integers are the smallest 7 consecutive composites, and below these 7 composite integers you can't get any this type of 7 consecutive composite integers. And this is very important, 7 consecutive composite integers. And now let us come to a very interesting topic, Twine primes. And without this, the prime number theorem will be incomplete. The above theorem shows that there are arbitrary long runs of integers containing no primes. You see this, you see here. On the other hand, primes may often close together. Note that the only consecutive primes are 2 and 3. And all of you know that the only consecutive primes are 2 and 3. However, there may exist pair of primes which differ by 2. These pairs of primes are known as Twine primes. The pairs are 3, 5, 5, 7, and etc. And look at, here is the difference of these 2 primes are 2. And these are some of the examples of the Twine prime pairs. The Twine primes are used to define a very special type of constant known as Brunn's constant. And in 1990, Viggo Brunn proved that the sum of the reciprocals of all the Twine primes, that is 1 by 3 plus 1 by 5 plus 1 by 5 plus 1 by 7 and up to so on, converges to a finite value, and this known as Brunn's constant. Yeah, this is a very interesting fact that although the sum of the reciprocals of the primes diverges, but the sum of the reciprocals of the Twine primes is convergent, and we will prove this result after sometimes. In contrast, the series of all prime reciprocals diverges to infinity. The Twine prime conjecture is that there are infinitely many primes P such that P plus 2 is also prime. In 2013, Itang Chang proved that there exists an integer n less than 7 into 10 to the power 6 such that there is an infinite number of primes P such that P plus n is also prime. A rather romantic story. The current record for the lower bound is that there exists an integer n less equals to 246 such that there is an infinite number of primes P such that P plus n is also prime. And now came to this conjecture, the Twine prime conjecture. And in mathematics, the statements which we can't prove yet, but we also cannot find the counter example to contradict this statement, and these are called, this statement is called the conjecture, and the Twine prime conjecture is a very important conjecture. There are infinitely many Twine primes, that is, there are infinitely many pairs of primes such as 3, 5, 5, 7, etc. And a more general conjecture is Polognac's conjecture, which states that for any positive integer n, there are infinitely many primes p such that p plus 2n is also a prime. And this conjecture is the general type of this Twine prime conjecture. The Twine prime conjecture is a special case of Polognac's conjecture with n equals to 1. If you put n equals to 1, then this conjecture will be Twine prime's conjecture. So this Polognac's conjecture is more stronger statement than the Twine prime conjecture. And the another unanswered question involves the Fibonacci sequence Fn, which is defined as f not equals to 1, f1 equals to 1, f2 equals to 1 plus 1 equals to 2. And in this way, f3 will be 2 plus 1 equals to 3, and the general form is fn equals to fn minus 1 plus fn minus 2 for n greater equals to 2. And all of you know this series. And the question whether there are infinitely many terms in the Fibonacci sequence, and it is still an open question in mathematics. Now let us come this very important theorem. This is called Brunn's theorem, and it tells us that there exists a positive constant c such that pi to x, and this pi to x is the Twine prime counting function, that is the number of Twine primes p less equals to x, and this is denoted by pi to x, and this is strictly less than c into x into log x by log x whole square. And the proof of this theorem is out of the scope of us, but using this theorem we prove this very important result: the sum of the reciprocals of all Twine primes is convergent, that is summation p, where these p's are Twine primes, 1 by p equals to 1 by 3 plus 1 by 5 and up to so on. And this summation will be approximately equal to 1.90216 and so on. And if you search in internet, you can check the accurate value of this Brunn's constant, which is called the Brunn's constant. Now let us come to the proof. It follows by using the partial summation formula. Summation p less equals to x, where these p's are Twine primes, 1 by p, and we can write this in this way: integration 3 to x, as the first Twine prime is 3, integration 3 to x d pi to t by dt, as all of these terms are in reciprocal format, so we can write this summation in this integration format. And now here is the first function is 1 by t and the second function is 1, so we write it in this way: 1 by t into integration d by t, and this will be pi to t by t, limit 3 to x plus integration 3 to x. The differentiation of 1 by t gives you minus 1 by t square, and so here is a plus symbol appear, and this will be pi to t, so this will be pi to t by t square dt. And this term, if you put these values, you get pi to x by x minus 1 by 3, because pi to 3, that is the number of Twine primes less equals to 3, is 1, and plus integration 3 to x, this integral, and this less than c into log x by log x whole square, because using this Brunn's theorem you replace this pi of x by this term and you get this log x by log x whole square, and this x will be cancelled out, and this will be same minus 1 by 3 and plus c into integration 3 to x. Here you get this term 1 by t into log t by log t whole square dt. And now came to the details calculation to get the final result. Yeah, so I tell you this term and this less than this, and now we calculate this integral, integration 3 to x 1 by t log t by log t whole square dt. Now put t equals to e to the power u, and then dt will be e to the power u into e power u du, and this values will be ln x, and this will be log 3. And if you put the values of t here, you get this term u square by e to the power u into e to the power 2u into, put this value of dt here, and you get this term. And now after some calculations, you will finally get this term u square into e to the power minus u du. And here the first function is u square and the second function is e to the power minus u. And we integrate this by our class 10 plus 2 level knowledge, that this will be u square into integration e to the power minus u du minus integration differentiation of u square into integration e to the power minus u du. And this will give you minus u square e to the power minus u, and this will give you 2u e to the power minus u du. And if you again differentiate, and if you again integrate this term by the previous manner, you will get finally minus u square e to the power minus u plus 2 into minus u e to the power minus u minus e to the power minus u, and the limits are log 3 and log x. And now came to this page. Yeah, so this will be minus u square plus 2u plus 2 e to the power minus u, and if we put these values here, we get minus log x whole square plus 2 log x plus 2, and e to the power minus u will be 1 by log x. And if you put log 3 here, we get this term. And now as we want to calculate this value for extending to infinity, so we calculate limit extends to infinity c log x by log x whole square. Look at here. We put limit extends to infinity in this term, and so limit extends to infinity, we want to calculate limit extending to infinity log x by log x whole square. And now you can easily see that this is infinity by infinity form, so use L'Hospital's rule. And if we calculate the value of log x by log x, limit extends to infinity, it will be easier. So we calculate this, and this will be limit extending to infinity by the rule of L'Hospital's rule. We differentiate these terms, we get this 1 by x log x by 1 by x, and finally this will be 1 by log x, and when extending to infinity, log x will be tending to infinity, so finally we get 0. So this term will be limit extending to infinity c log x by log x whole square will be c into 0 equals to 0. Now came to this term log x whole square by log x, and then 2 log x by log x, and then 2 by log x, and we will show that all of these terms will be 0 when extending to infinity. Here look at this limit extending to infinity, this term, and using the same procedure, the L'Hospital's rule, you can see easily that all of these terms will be 0. If you calculate this, you will get the 0. So limit extending to infinity, this integration 3 to x 1 by t log t by log t whole square dt, this will be finally log 3 whole square plus 2 into log 3 plus 2 by log 3, because this term, we evaluate this, that this term will be 0 when extending to infinity. So only this part will remain. So finally, we get that this summation p, where these p's are Twine primes 1 by p less than 0 minus 1 by 3 plus this term, and this is a finite value, and this is less than infinity. So we finally obtain this result, and so we finally proved that the sum of the reciprocals of all Twine primes is convergent. So this is a very nice proof. Now came to another conjecture. This is called Bertrand conjecture. For each natural number n greater or equals to 2, there exists a prime number p such that p lies between n and 2n. The above conjecture has been verified up to large values by Bertrand, who formulated in 1845. It was proved by Chebyshev in 1852. As a consequence of this conjecture, one can show that the nth prime doesn't exceed 2 to the power n for n greater or equals to 2, and this is the theorem. If Pn denotes the nth prime, then Pn less than 2 to the power n for n greater or equals to 2. And we will prove this theorem by using this Bertrand conjecture. Now let us come to the proof. We use induction on n. The assertion is clear from n equals to 2, and assume it is true for n equals to k greater or equals to 2. And then by Bertrand conjecture, there is a prime p such that 2 to the power k less than p less than 2 to the power k plus 1. If you put this n equals to 2 to the power k, you will get this result. This n equals to 2 to the power k, and this will be 2 into 2 to the power k, that is 2 to the power k plus 1. And then this pk is less than p, therefore we have found a prime bigger than the first k primes, which is less than 2 to the power k plus 1. And finally we prove this theorem. And now this is a very important conjecture, that is Goldworth conjecture. And this tells us that any even number greater than 4 can be expressed as a sum of two odd primes. So any even number greater than 4, we can express it as the sum of two odd primes. And here are some examples. You express 6 as 3 plus 3, 8 equals to 3 plus 5. You can write 10 equals to 3 plus 7, and you can also write it is equal to 5 plus 5. One can take as large as an even number as possible and find two primes of which the given number is a sum. However, a proof has been elusive for more than 240 years since Goldworth first put this question to Euler, who was one of the leading mathematicians of that era. A similar open question is that any even number can be written as the difference of two primes. For example, you can write 2 equals to 5 minus 3, 4 equals to 7 minus 3, 6 equals to 11 minus 5, and in this manner. Note that if Goldworth conjecture is true, then any odd integer n greater than 7 will be a sum of three odd primes. And look it very carefully. Suppose n minus 3 is an even integer bigger than 4. Hence, we can write n minus 3 equals to p1 plus p2 for two odd primes p1 and p2 by Goldworth conjecture. And then this n will be equals to 3 plus p1 plus p2. And in a major progress, Two genius mathematicians Hardy and Littlewood showed that under another conjecture known as the Riemann Hypothesis, every sufficiently large odd integer can be expressed as the sum of three odd primes, that is in this way. It has also been proved that almost all even integers satisfy Goldberg conjecture in the following sense. That is, if g of x is the number of even integers n not exceeding a real number x, such that n doesn't satisfy the Goldberg conjecture, then limit x tends to infinity, g of x by x equals to 0. That is, to get the probability of these types of even integers that doesn't satisfy the Goldberg conjecture is very less. However, note that the above result doesn't rule out the possibility that there still may be infinitely many even integers which are not expressible as sum of two primes. The vanishing of the above limit merely says that such occurrence will be very rare. So my lecture is completed. Thank you all of you for attending this lecture, and thank you to our sir for give us this opportunity to do this lecture. Thank you.
Thank you, Tathagata, for your nice talk. Yes, it's really good, and I hope that everybody enjoyed it. So now it's a turn for Anubhav to share your screen to continue the same thing with more detailed the part that he has already in his mind. So Anubhav, can you please share your screen?
Yes, sir, I'm sharing. Yes. Is my screen visible to all?
Yes, it's coming.
Okay.
Yeah,
Yes.
it's visible.
So, as my fellow friend Tathagata has talked about some heavyweights, conjectures, and theorems, but I would not like that much. I would say the prime number theorem like storytelling, and I would like to interact all of you with me. So at first we know that the prime numbers are the numbers which are divisible by one and itself, and there are two different natural numbers, that is complex composite numbers and prime numbers. So the some first 20 natural numbers, the prime numbers among 20 natural numbers are 2, 3, 5, 7, 11, and so on. So now I would like to suggest you to imagine a, a tree within a square field like this. Let us see, this is a square field, and there is a infinitely high tree is presented in the center of this field. So there are leaves, many leaves are there in this tree, and the tree leaves are dropping down the tree, and you will find that the trees, as the tree leaves drops in the bottom, you can find the density of the leaves are very dense in the near the tree, and as you gradually go far the tree, you will find the density of the trees, leaves of the trees will faded away. So that is how the primes are distributed among the natural numbers. If we make a square and take make it like this and write the natural numbers from the center, we will find a picture like this. Let me show this picture. Yes, this is the this is a circle, but I will take I will let you imagine that this is a as a square field. So this is the blue dots are the prime numbers among the natural numbers, and this red line is the prime of Euler primes, that is of the form n square plus n plus 41. So you can see the primes are more dense in this center, and as the number is sufficiently large, the prime distribution of this prime has been scattered and less dense. So in the 20th century, the great mathematician Terence Tao have gave a lecture uh, in a in his lecture. He has discussed about the structure and distribution of the primes, and this is related to the Riemann Zeta function and its zeros and all of like Riemann Zeta function and related to the Riemann hypothesis. So, but again, now I am uh, trying to go to this prime number theorem. Let us see some interesting tables. Okay, this this table is from Wikipedia. So let here x denotes the number of natural numbers, and pi x denotes the number of primes before that. Oh, so previous this I would like to define the prime number counting functions. Okay, so what is prime counting functions? Let me show this. What is prime counting function? So prime counting function is denoted by pi n. Don't uh, take it as a irrational number pi. This is just a notation, as pi n is a prime counting function that gives the number of primes less than or equal to n. So basically we are trying to find a good expression for this prime number theorem. We are basically trying to find a good expression for this expression pi of n, and that this is prime number theorem. So let us show this table again. So here is x is equal to 10, and pi x, as you know, this is a prime counting function less than or equal to 10. Now we have what we have, let x equal to 10. Then what we have, the prime numbers before x is mm, 1 is not prime, 2, 3, 5 and 7. So before 10 we have these prime numbers, and so pi of x equal to 4. And as we talk pi, so let us take at first pi of 2. What is pi of 2? The before the number of primes below or equal to 2. So we have one primes less than 2, that is 2. So pi of 2 is 1. And then pi of 3, the number of primes less than or equal to 3. We have two primes, 2 or 3, 2 and 3, that is 2. And so on. 5 is 3. Pi of 6 is also 3. Pi of 7 is 4, equal to pi of 8, pi of 9, and also pi of 10. So the prime counting function is this type. Don't take it as a prime generating function polynomials. I have also showed that the prime generating functions are those polynomials which can generate prime numbers, but these prime generating functions are that generates prime numbers scatteredly. Like this, we have due to Euler, we have this polynomial, the best polynomial which can give the prime numbers from for n equal to 0 to 39. And according to Dirichlet arithmetic progression, that is, we have this progression: a is a prime, then a plus nd is also a prime. So this arithmetic progression we have prime numbers, and we moreover the green tau theorem shows that there exists a pair of a and b with this property that ln equal to an plus b is prime for any n from 0 through k minus 1. And as of 2020, with the best known result of such type is k equal to 27. That is, this number and this number has yield a prime number for n equal to 0 to 26. Okay, so you don't take mistake with this prime generating function and prime counting function. So the best motivation for us to find the prime number theorem is that we have, if we if you are asked that you are given a natural number n is sufficiently large, then you are asked to find the number of primes below this number n. So we are basically focused on these questions only, so that how we can found the number of primes below natural number n. And back to this, see, illustrationists have also find his best algorithm for this to find the prime numbers below a small natural number. That is, you can see here that this is a GIF of illustration, sieve of illustrationist to find the prime numbers less than small natural numbers. If you get a prime number like this, natural number like this one, maybe 1 trillion or 1000 trillion, whatever. So if you try to find like this, this will be a lengthy process, and you will be getting irritated. So what we do in sieve of illustration is we will write these types of natural numbers in this arrow and rectangular array, and then we block. This is not a this GIF is not working, so I would so I take this thing. Okay, so how can I will discuss about the sieve of illustration. So let's make a list of consecutive integers from the smallest prime to through n. Suppose you are finding this uh, number of, okay, suppose like this 2 3 4 and up to this n number. We have written n consecutive numbers, and then we are blocking, taking the first prime number, that is 2, and write this. And after this we are blocking this all the multiples of 2 like this. Okay, like this. And then again we are considering the next prime, that is 3, and writing this. And again like this we are blocking the multiples of 3, and so on. After this we are taking the next prime, that is 5, and blocks this all the multiples of 10. Let me show the table. Okay, this is, let first block this 2 4 6 8 and 10 like this type, and all the block, or we have all blocked the multiples of 2. And then 3, we have also blocked 6 in number 2, but again 8 9 12 and so on, and write this 2 3 5 and 7. Basically he had basically we have to uh, make this count for n equal to root n. We have to find we have to go through this process up to n equal a p equal to root n. Okay, how? the process is this. And make a list of consecutive integers from the smallest prime 2 through n. Initially let p equal to 2, and we are letting first the p as a prime p equal to 2, and make a sequence of the multiples of 2 up to n, like 2n, 3n, and like this. Then find out the next smallest integer, that is 3, and which is greater than 2, and we are taking that is p equal to 3, and that is not marked yet. Then replace the value of p equal to that number and repeat the third process. This third process, that is the multiples of this. After this process terminates, the composites are all marked and the remaining ones are the prime numbers equal to this thing. So after we take p equal to uh, root n, we don't have to go further, and we all get the prime numbers. This is a sieve of Eratosthenes. It is not working for large number of n. So we have to find the formula for this, to find this, the number of thing, the number of primes. And so how this is going to work. So now uh, now I would like to tell one of you the as how this the graph of y equal to log x. Can anyone say me the tell me the graph of 1 equal to y equal to log of x? Hello, hello, are all of you listening? Hello,
Yes, yes.
hello. Can anyone tell the how the log of x graph looks like?
It increases slowly and it has asymptote in the y-axis.
Yes,
It
that
cuts
is
the
like this,
x-axis at
right?
one. Yes.
This is 1 0, and the uh, the graph of 1 by log x just reflects like this, right, Pratik? Yes. And now, so this table again, see, when x is equal to 10, that is natural number, and pi x equal to 4, and when x equal to 100, this is pi x equal to 25. Okay. uh, and 10 cube, and that is 1000. Pi of x equal to 168. So let's take this. Pi of 10 equal to 4, pi of 100 equal to 25, and pi of 1000 equal to 168. Okay. So now, uh, now, now go to this thing. Okay. As you are seeing this kind of spirals here, uh, and we have found a relation between the center, between the distance of the center, like this, from here to here. Okay. This time. Okay. Just a minute. Okay, sorry for the inconvenience. Now, so if you see this, the distance, let's take this distance from the center is r, and the number of rotations as phi. So we are taking the number of rotations as phi, and let's take this kind of things we are talking about. Okay, the number of rotations and this is r. If we plot this thing phi over r, we will see that this is looks like the one of uh, y equal to 1 by log x. This kind of graph we will see. So how this is related? So if you see we have this kind of prime numbers and over there, and we have all the prime numbers here. We have marked these prime numbers at blue colors, and the natural numbers are over here. So if we are taking n natural numbers and the number of prime numbers is pi of x, then we are dividing this, that is the density of these prime numbers, and we get this is almost equal to 1 by log x. 1 by log x. And let us talk about this, the area of this thing. According to the integral formula, we have this area, that is density multiplied the density, that is the density into multiplied by uh, x. Okay, so from this we are getting pi of x equal to x into this density, that is 1 by log x. And this is I am writing this is equal, but this is asymptotically equal, and Tathagata has will define this asymptotic definition of something, and this is the prime number theorem, that is pi of x, the number of primes less than equal to x something, this is equal to asymptotically equal to x by log x. This is the basic definition of the prime number theorem. Okay, this is the basic definition, but in later uh, uh, when we look at the history of this thing, you will have considered the Riemann zeta function before Riemann have uh, discovered this function for complex variables. We see that Riemann Euler has considered the Riemann zeta function and the distribution of primes for amongst the rational numbers, although Riemann has not discovered the zeta function for this. But after this, everyone has taken attempt to prove the prime number theorem, but no one succeed until the 20th century. Anton Felkel and Juris Vega has made a table for factors, and with this factorization table and the list of primes, D'Alembert has listed the prime numbers between 10 lakhs to 2001 to 40 lakhs 31 in the last 18th century. After that, Legendre had go through this table and make a good uh, approximation for this prime number theorem. That is, what he does, that pi of x by, he did log x, he replaced the log x by log x, a log x minus plus b, and after that he found a equal to 1 point something. He found that a equal to 1 and b equal to minus 1.08366. He found that a equal to 1 and b equal to minus 1.08366. So that is, the expression becomes what, log x minus 1.08366. This after that and this is the extract from the table of the uh, Felkel and Vega. And after that, Gauss, in the age of 16 and 15 or 16, he considered this problem, and after that 18 and 38, Dirichlet came with his own calculation and with the logarithmic integral Lix to approximate the expression. And what is the logarithmic expression integral? Li of x is, sorry, this is Li. This is Li of x. This is Li of x, and this is 2x 1 by t dt. One by t dt, and that is pi of x by Lix is when limit x tends to infinity, pi of x limit tends to 1, and this is also an expression for prime number theorem. Okay, after that, now we are discussing about the history of the prime number theorem proof, but we are not showing the proof. Actually, this is beyond our syllabus or scope. The prime number theorem proof is very lengthy and very complex. It would include the complex analysis, that is the Riemann zeros of the Riemann zeta function. Okay, this, what is this? In this in the years of 1848 and 1850, Chebyshev had tried to prove the prime number theorem, but he only succeeded to show that the limit this pi of x by ln x is actually exists, but he could not show that uh, the limit is actually equal to 1. But in but his paper has helped to directly help to the Bertrand's postulate that every n greater than 2 there exist primes between n and 2n. And I would now like to show that the prime number theorem as a probabilistic approach, that we know, whoever had a course of basic probability, or we have the basic probability course in 12 standards, that the classical definition of a probability is p of x equal to p of probability of x equal to the number of favorable number of cases for the event x, and the total number of cases is here. Okay, so when we are taking n number of natural numbers, we are taking n natural numbers and then find the number of primes less than or equal to n, that is pi of n. So we can take feed this thing into this picture, and that is we are taking pi of n number of prime favorable cases, and then the total number of cases is n. That is the probability. This is the probability of getting any any number of this thing. Sorry, we are taking a random number from these n natural numbers, and what is the probability of getting the number is prime, that is 1 by log n. So so sorry, so this is a probabilistic approach to getting into this prime number theorem. And this what is Barton postulate is that we get a prime number, at least one, that is n to the numbers between n to 2n. Okay, so we are taking now we are taking 2n instead of n, and what is the probability? This is pi of n divided by 2n, into 2n. And compare these two, we are getting the probability. So at least we are getting the probability of at least half. So there is a half chance to get a when we are taking the first n natural numbers and take a random number, and we are trying to find this the number is whatever prime or not, and then we are taking the double numbers, that is 2n, and trying to find the same natural number uh, to uh, mm, to be a prime number. There is a probability that is half. uh, so I think this is clear to you. And the Riemann has wrote a paper on prime number theorem that is named on the number of primes less than a given magnitude. He introduced new ideas related to the zeros, as I am talking about before, and the zeros of his zeta function for real arguments, and this helps 19th century mathematicians to prove the actual PNT. And after that, extending the Riemann's ideas to proofs of this asymptotic law of the distribution of prime numbers were found independently by Hadamard and Vallée-Poisson. Appeared in the same year of 1896, but the proof includes very complex analysis and but the main step of this function is the Riemann zeta function is non-zero for all complex values of the variable s that have the form a is equal to 1 plus uh, it. So we know this Riemann zeta function is like this. We know that Riemann zeta function is like this, sum over n 1 by n to the power s. And this is natural number, and s is a complex number. But consider s is equal to 1. So this thing over the natural numbers, and we know this thing is this series is non-convergent, it diverges to this thing. And how the Riemann zeta function is related to the prime number, I will show you just now. Suppose take this thing, and this is due to Euler, that pi of 1 minus 1 by p the power s inverse, some definite multiplication over p. How this is, consider this thing, 1 by p, 1 by p square, 1 by p cube, and this is a geometric series, right? And this is 1 by 1 minus p, and and this is true for p less than equal to 1 and less than equal greater than equal to 0. And as the primes start from 2, and then this is true for, sorry, this is true for all primes, right? So we have this geometric series, and after that we have this geometric series 1 by 1 minus p to the power s, right? And this is how this Riemann zeta function is related to this thing. So again, now I formally define this statement of the prime number theorem. Let pi n denotes the number of primes less than or equal to n then we can approximate it by this term pi of n by ln n. This shows that now number of primes is asymptotically equal to n by ln n. This is mathematical expression for this thing, and in other words, limit n tends to infinity, pi of n divided by n by ln n equal to 1. And I have said this thing, and now we are guessing the nth prime, and this is a consequence for the prime number theorem. Okay, so we have let number, and from the asymptotic thing we have what we are getting n, sorry, n equal that is 1 by log n, and this implies n equal to approximately this equal to pi n log n, and we are taking n equal to prime, so the number of primes before n is n, and then therefore n is the nth prime. So Pn, if we denote Pn as the nth prime, so Pn equal to n log n. We are getting this formula, and this is also a fast formula, and there are also some variations of this formula, but I am not going to into this. Okay, so that's all for me, and now I would like to thanks our sir to giving me such an opportunity to talk about the prime number theorem, and all of you to listen to this. Thank you, sir.
Yeah, so I just have one thing that if you have any question, you can ask me, because I skipped this part because Anubhav has the lecture. So if you have any questions, so you can ask both Anubhav and me.
So thank you both the speakers, Tathagata and Anubhav. Both of you have done really a great job. Now, if you have any doubt or questions, you are free to ask. Unmute yourself and ask the question to both the speakers. They have really given a nice presentation, and a nice way of speaking and nice way of teaching. So I really enjoyed. So in our last class also, we enjoyed the two lectures. This class also is very good, and I think in the next class we should go for Akash, and maybe Swapnil may also join as mentioned. So Swapnil's portion will not be within the syllabus, but it should be known to all, because that's basic mathematics, and for the remaining part it will be within the syllabus, linear Diophantine equation, that will be delivered by Akash. So now if you have any doubt or questions, you are free to ask.